seekers of the truth, rebels of the everyday. Welcome to part 7 of motion along a straight line. Free fall acceleration. A type of motion along a straight line, but in free fall, that is, along the vertical axis. To explain this topic, I want to use the short clip you saw at the beginning of this video. Also, we'll use the same equations we developed in part 6, but in this case, our acceleration will be g, the free fall acceleration rate of objects near the surface of planet Earth. Everything else works just the same. So here we have a cannon at the park. This cannon fires a round shot along the vertical axis. What we will do in this video is to analyze the motion of the round shot based on some initial data and what we can figure from the clip. To begin with, the initial velocity of the round shot when it leaves the cannon is 12 meters per second. With this information, let's find number 1, how long will it take the round shot to reach its maximum height? Number 2, what is the maximum height of the round shot? And number 3, how long will it take the round shot to reach 5 meters above its release point? As I already said, everything about the equations we already developed continues to be true for free fall acceleration motion. The only thing that changes is that instead of a, or acceleration, we use g, the free fall acceleration rate of objects on planet Earth, which by the way is a constant, specifically 9.8 meters per second square in metric or 32 feet per second square in imperial. We'll use metric for this example. For the purpose of this explanation, we are going to neglect the air resistance and any other force acting upon the round shot. Okay, let's go over this using the equations we already know. But before starting to write equations and throw numbers here and there, let's analyze the situation to understand what we have in front of us. First of all, the round shot leaves the cannon with an initial velocity of 12 meters per second. Without initial velocity, the round shot would not move. So there has to be initial velocity in this case for the round shot to move vertically. Also, g, the free fall acceleration rate on Earth, acts toward the center of the planet. So if an object goes from bottom to top, g is in the opposite direction of the motion, and therefore, if no other force is providing thrust to the round shot, its velocity decreases. Eventually, it slows down until its velocity is 0. And guess what? At that point, it reaches its maximum height. Thus, it is important to notice that the maximum height occurs when the final velocity is 0. Once the round shot reaches its maximum height and completely stops, it begins to fall because the acceleration rate, g, points toward the ground. The motion direction now changes to be the same than g, since no other force is acting upon the round shot than its weight. Thus, the round shot accelerates as it moves down with constant acceleration g. The round shot finally reaches the floor and its velocity goes back to 0 again, but 1 instant before it reaches its maximum velocity. So, having said this, we can now solve this problem as we understand better what we have in front of us. The first part is to find the time it takes the round shot to reach its maximum height. For this, we use the equation that defines average acceleration, and from here, solve for time. So we have average acceleration equals final velocity minus initial velocity divided by final time minus initial time. First of all, and since acceleration is constant, the average acceleration and the acceleration at any instant are the same. Thus, we can rewrite this equation using acceleration instead of average acceleration. Also, we already stated that the acceleration we'll use is the free fall acceleration rate of objects on planet Earth, which is g. And since we're looking for the maximum height, we can make final velocity 0 because from our previous analysis, we know that when the round shot reaches its maximum height, its velocity is 0. Also, we can make initial time 0 because that's when we start the clock. Thus, we have the acceleration is initial velocity negative divided by final time. If we solve this equation for final time, we have that final time is initial velocity negative divided by the acceleration, which is g. Thus, the time it takes for the round shot to reach its maximum height is like this. At this point, you might be thinking that we will get a negative time, which would be weird, but it is important to remember that when the round shot goes up, g is opposite to the motion, and that is why the round shot eventually stops. If this is true, then g must have a negative sign as it points in the opposite direction of the motion. Thus, we add a negative sign to the equation in g, and we get a positive time. Substituting the values, we have this. To solve the second part of the problem, we need to find the maximum height. To do this, we use the second basic equation we developed at toysandphysics.com. Thus, initial height is 0, since that will be a reference for the motion. Substituting the values, we have this. Noting that measurement units are consistent, let's submit them by now. The maximum height is 7.35 meters. The third part of the problem is to find how long it takes for the round shot to reach 5 meters above its release point. To do this, we can use the same equation we used to solve the second part of this problem, but now we'll solve for t instead of final height, since we already know that final height is 5 meters. Thus, we have this. Initial height is 0 again. As you can imagine, this will become a quadratic expression that we will solve for t at 5 meters. Rearranging things here to make it look like a quadratic expression, we have this. To solve this, we'll use the quadratic formula, which goes like this. Substituting the values, we have solving the inner portion of the square root, we have this. Thus, we'll get two different values of time. T1 equals 1.91 seconds and T2 equals 0.53 seconds. There you have it. This is how we analyze the motion of an object moving on the vertical axis. The very same type of analysis is what scientists at NASA and other companies launching rockets do when they prepare for sending people to space. In those cases, you don't neglect air resistance and other weather conditions. And while the analysis is more detailed, the principles are just the same. So, is that cool or what? Just a disclaimer, the cannon, the explosion, and the round shot were all fake and created using a computer. I'm sure you noticed that, but it is important for me to say that so you don't try this at home. For now, and as always, I would like to invite you to subscribe and click on the bell icon so you know when I upload a new video. Also, if you like this video, please give it a thumbs up to support the channel. We'll catch up on the next one. Bye for now.